Good afternoon. Welcome to another joint seminar of Microsystems Technology Laboratories and the MIT AI Hardware Program. I'm Jesus del Alamo, Professor of Electrical Engineering. And today we're happy to have Professor Shimeng from Georgia Tech, who is giving a talk on ferroelectric devices, circuits, and architectures for AI hardware design. I'm delighted to see that this talk has attracted so much attention. So Professor Shimeng is the Dean's Professor of Electrical and Computer Engineering at Georgia Institute of Technology. He received his bachelor's degree from Peking University in microelectronics and master's and PhD degrees from electrical engineering at Stanford University. After graduation, he was assistant professor at Arizona State University, and since 2018, he has been with Georgia Tech. His general research interests are semiconductor devices and integrated circuits for energy-efficient computing systems, with particular expertise on emerging non-volatile memories for AI hardware and 3D integration. He's received numerous awards, and I will just single out here the NSF Career Award, the Semiconductor Research Corporation Young Faculty Award, and the Intel Outstanding Researcher Award. And he's also a fellow of the IEEE, and his nominations cites in particular his contributions to non-volatile memories and in-memory computing. Shimeng, it's a real pleasure to have you with us today. Thank you for coming.
Thank you, Jesus, for the nice introduction. And today is my great pleasure to be here on campus of MIT to share some of our research progress in the field of the ferroelectrics. So in my talk, I try to advocate a research philosophy that is to co-design the device, circuits, and architectures for this important research area that is AI hardware design. So if you look at the general AI hardware trend, of course, we have those amazing applications around us, like computer vision for the autonomous driving, or the large language processing for those, ChatGPT kind of applications. So underlying those applications, we have those hardware platforms to run those algorithms efficiently. So here, of course, if you look at the industry standard or the mainstream technology today, it's still dominated by the GPU. And we see more and more companies are designing their own custom chips to further accelerate those workloads. For example, here we have Google's TPU, which is based on a digital historical array, where we have the digital MAC to do the compute-intensive operations, where the weights are stored on the global shared SRAM buffer. So still, we have a lot of data movement on chip, even though we here optimize the data flow and try to reuse the data. So this is more like a near memory computing solution. If you look at the energy efficiency, I quoted here in terms of the TOPS per watt, tera operations per second per watt, essentially the throughput divided by the power. So here, this near memory computing solution is typically on the order of a few single-digit TOPS per watt. So what is limiting this overall energy efficiency? That is a memory wall problem that is well known to the computer architecture community, where you have to fetch the data from the memory units, especially from the off-chip DRAM. Then we're going to spend a lot of energy to move the data around. So then the alternative approach or paradigm for the compute is to enable this in-memory compute, where we're going to employ a weight stationary data flow, try to, let's say, map the neural network weights into the memory arrays on chip, and then we just move the input and output activations around. So we can save a lot of data movements. Especially, we can turn on multiple rows of the memory array to do this parallel computation to further boost the throughput as well. So here, in terms of technology choice, you can use CMOS technology, for example, SRAM, to do this job. Of course, SRAM, you can enjoy the scaling to today's 3 nanometer and beyond. That's why SRAM still maintain a competitive solution, especially for training and high performance in the high performance computing environment like a data center. But if you look at the edge AI inference application, I would say the non-volatile memory solution could be preferred in those domains, because SRAM is always leaking, even though the system might be in the standby mode, waiting for the signals to awake the inference chip. So in that case, we can store all the weights on those non-volatile memory. We can power off the chip and during the standby, and then we can instantly turn on the system to do the inference. So we have been working on RAN technology for many years, and actually we had collaboration with TSMC. We taped out 3 generations of the RAN-based computing memory chip with TSMC 40nm process, and we realized some of those functionalities with the RAN chip. But we suffer from some disadvantages of this technology, particularly due to the variations of the RAN and also the relatively low resistance of the RAN technology, especially at the on state. We only have a few kilo ohm. Therefore, when we turn on multiple rows, we are going to get like more than hundreds microamp current from the column. That will increase the instant power of the system. So what could be the next generation of the technology? So here we bet on the ferroelectric devices, and I will show you the state of the art in terms of the industry and also our research progress in this domain. So here are some basics for the computing memory. So essentially, it's a mixed signal compute scheme. For example, if you have a neural network model, then you can map the input activations as the voltages that could turn on multiple rows of the memory array. And then the weights could be mapped as a conductance of the memory cell. So the input voltage multiplied by the conductance of the cell, we will get a current. And then we can naturally sum up the current along the column. So at the end of the column, we have the weighted sum current, which represents the dot product between the input vector and then the weight matrix. Of course, we may have to do some like post-processing, for example, to digitize the analog sum current to the digital bit through the ADC and also the shift and add to reconstruct the weight significance depending on the precision of the partial sum. So in terms of the memory technology here, we can have different flavors. As I said earlier, we can still use the CMOS technology like SRAM, but in many cases, we have to customize SRAM. For example, use this 8-transistor SRAM cell to have the decoupled read pass, because when we turn on multiple rows, then we want to minimize the read disturb. So we have to decouple the read and the write pass. And then if you want to have more compact solution, instead of 8 transistor, then you can do 1 transistor, 1 resistor approach, where this resistor could be RRAM or phase change memory, where you can tune the resistance of the memory cell. And then if you look at the most compact solution for this, would be a single transistor solution, where we have the ferroelectric field effect transistor, FEFET. The threshold voltage of the FEFET could be tuned by the polarization of the gate stack. Therefore, we can have different channel conductance to represent the weight. So essentially, we prefer to have multi-level states to serve as a multi-level bit of the weight. So let me quickly go over some basics of the ferroelectrics. So as you know, ferroelectric is a subset of the dielectrics, where the spontaneous polarization occurs. Of course, historically, the ferroelectrics are most based on the perovskite material, for example, PZT or SBT and so on. But those materials are not scalable. They have to maintain larger than 100 nanometers thick to maintain the ferroelectricity, which is not very compatible with advanced CMOS. For example, if you want to integrate that to the gate stack, your gate stack cannot be 100 nanometers thick. So about 13 years ago, there was a first report from the NAM lab from Germany. So the hafnium oxide system could show the ferroelectricity if it's properly doped with certain dopants to create this so-called orthombic phase. So depending on the crystal orientation, then you may have the built-in dipoles with those 2 possible configurations. And therefore, you can have this ferroelectricity in the hafnium oxide system. So of course, some quick recap of the polarization. That is the surface charge density of this material system, right? So if you withdraw the electric field, if the dipoles are still lined up, then at the surface, you will get certain amount of the charge density in terms of the units, like microcoulomb per centimeter square. And then at the 0 field of voltage, you have this remnant polarization. Then that could be your memory window between, let's say, on and off states. Of course, this is typical polarization versus the electric field hysteresis loop. If you characterize the ferroelectric materials, you expect to show this kind of PV loop or PE loop Of course, there are different components to this curve. One is the polarization switching. The other one is a normal, displacement current, charging and discharging. If you want to integrate the ferroelectrics into the device components, then actually you have different flavors to do the integration. So here we have a family of the ferroelectric memory. The first one is what we mentioned before, FE-FET. So basically you integrate the ferroelectric stack into the normal MOSFET structure. So here we tune the threshold voltage to create the memory window. And the other way is to integrate the capacitor to the drain of a normal access transistor as 1T1C structure. So this is also called FE-run. And in this case, we are using the large signal polarization switching current versus the smaller displacement current as a memory window. So essentially, we are going to destruct the state when you read out. So this is called the destructive read. And the third category is something new, which was proposed by our lab. So this is called non-volatile capacitive mode to read out the capacitance of the ferroelectric capacitor. So here we are going to use a small signal CV asymmetry to create this memory window. And then we use small signal, therefore it's non-destructive read. And we will talk about that in more details later in the talk. In terms of where you can integrate the ferro, there would be the front of the line integration, where you insert the ferro to the gate stack, for example, in the FE-FET with the silicon substrate. Or you can do the ferro integration at the back end of the line, which means on top of the interconnects. So you can get the FE cap on top of the interconnect, and also you can do the ferro-FET using the non-silicon channel as a back end of the line. For example, typically people integrate that with the oxide semiconductor as a back end line oxide FE-FET. So here are some fundamentals of the FE-FET. We already mentioned that before, but if you look closer to this cartoon figure, so if you program the ferro, let's say apply a positive gate voltage large enough, you can polarize all the dipoles down, then those dipoles will easily induce the inversion of the channel. So typically it's unfed, okay? Then you get electrons in the channel. That means your threshold voltage is lower. So if you look at IDVG, then it should be something like this. And if you reverse the voltage polarity, let's say polarize all the dipoles up with a negative voltage, then the channel could be in accumulation. Then the threshold voltage will be higher, so like this. Of course, you can partially polarize those by using some intermediate voltage. So let's say some dipoles up, some dipoles down, then you can get those intermediate states. So we can use this as a mechanism to map the multi-level, let's say, weights into the multi-level channel conductance. So compared to the charge trap or the floating gate flash transistor, the FE-FET could exhibit the advantages like lower switching voltage and faster switching speed. And then compared to the resistive memories like R1 or phase change memory, then the FE-FET could have much lower write energy, because here you use field to drive the polarization switching. This is like a transient switching. So it's unlike the R1, it's like a current driven, so you have to pass a lot of power. So this one is field driven, so that's why the energy is low. And also for the read, we can bias the gate voltage, therefore we can increase the unstated resistance above tens of kilo ohm, even close to 100 kilo ohm. Then this is also much higher resistance compared to R1 or phase change memory in the unstate. That's why the read energy could be also lower. So in terms of the industry R&D status, so over the past decade, the companies really invest into this technology. For example, GlobalFoundries has been pioneering in terms of the integration. So they have risk manufacturing of the 28 nanometer high-k metal gate platform-based FE-FET, and also 22 nanometer FD-SOI-based FE-FET. And actually, our lab has very close relationship, or let's say collaboration with Global Foundry. For example, here, this is what they ship to our lab, the 12-inch wafer with 28 or 22 nanometer FE FETs for us to do further categorization in our lab. And also, for the back-of-line FE FETs, so for example, Intel and TSMC, actually also one of my collaborators, will also present their updates with the back-of-line FE FET in the upcoming IEDM conference with oxide channel. In their case, it's IGZO. And there are some challenges moving forward in terms of the FE FET technology. So one of that is variability. So especially when you scale down the technology load and then the size of the gate area, that will matter because the multi-domain nature of the ferroelectric, especially when your thickness is about 10 nanometers thick in terms of the ferro thickness. So then another challenge is the reliability, especially for the front-of-the-line silicon channel. Then you have the interfacial layer between the ferro and then the channel. That will create a lot of trap. And then especially during the cycling, and you get a lot of electron trapping there. And then the last challenge is to move forward, let's say, because of this high rate voltage, especially for the front end of line silicon channel, you have like around 3 volts in terms of rate voltage. This is higher than the typical logic core VDD, or even higher than I/O voltage of advanced CMOS logic. So this will present some challenges in terms of the circuit design. We have to have specialized on-chip charge pump circuit to drive this high voltage moving forward. So let's switch the gear a little bit to look at FE run. This is also a hot topic these days, the 1T1C. So Sony has pioneered in the FE run integration, and they have done this, for example, at 130 nanometer with 64 kilobits. I think this is from the VLSI 2020. So here the MFM cap is integrated as a drain contact via of an access transistor. And then if you look at the Micron's recent announcement from the last IEDM, so they reported 32 gigabit FE run. So they're using the DRAM process. Micron is a memory vendor, then they have the specialized DRAM process. But in this case, they integrate 2-layer 1T1C and with the polysilicon as the access transistor. This is because for the ferro, you don't need ultra low leakage, right? Unlike the DRAM, you need a specialized like a DRAM transistor. But for ferro, it's non-volatile memory, then they can use a polysilicon with a higher leakage current. Then you can do this 3D integration with 2-layer 1T1C at the back end of the line. So those are the amazing announcements from the community in the recently. So, but there's one challenge for the FE run from the application point of view. That is read destructive nature. So every read cycle, you are going to consume the endurance. So even though Micron reported 10 to the power 12 cycles, let's say endurance cycles, but if every read is going to consume the cycle, then your lifetime won't be long because every read, you read it every like tenths of a nanosecond, then 10 to the power 12 actually doesn't last very long. So that's a challenge. So that's why we are interested in non-destructive read mechanism. Okay, so let me quickly go over the 4 topics I'm going to talk about in the next 30 minutes. So the first one is the fundamental device physics of the ferroelectric field effect transistor. We figured out there's a history effect in the minor loop switching. Initially, we thought that we can tune the FE FET into multi-level states to do the continuous training, but turns out there's a big challenge to do that due to the device physics. So I'll quickly show you what prevents us from doing that. So if you want to tune the device into the intermediate state, for example, you have different trajectory here to program the device from, let's say, S0, the ground state, to different intermediate states. So this is by simulation first. So this is based on the typical precise model. And we have bigger loop, which is the blue curve. Let's say we start from S0 and then program the device to the S3. and then we switch it back to the S2, and then we switch it back from S2 to S1. Okay, so this is bigger loop. And then in the smaller loop, which is the red curve here, we start from the S0 and then go to S2, and then from S2 to S1. So here you will notice that for the same transition from S2 to S1, the switching voltage here, the VD and VC, actually are different, depending on whether the device has gone through S3 state or not. So that means there's a history dependency here. So this is simulation, and then we verify that in experiments, first from the FE cap. So we try different trajectory, different combinations, different sweep frequency, and the different sweep polarity. This behavior seems universal there. So here the switching voltage is different. And then we also verify this from the FE FET. As I said earlier, we have access to GlobalFoundries 28 nanometer FE FET, the wafer in our lab. We tested similar like larger loop and smaller loop in the FE FET. So here I won't go into the details of those graphs, but I just want to draw your attention. Let's say 2 examples here. Because for the FE FET, we will read out the drain current as a mechanism to determine the intermediate states. So here, for example, in this larger loop, in order for us to switch from S2 to S1 state, let's say the IDVG curve, right? So here from the red one to the blue one, then here we're going to apply elective gate voltage like 2.8 volts to switch from here like 5 microsiemens to 0.2 microsiemens. And then for the smaller loop, if we want to achieve the same switching from the S2 to S1 states, then we need to apply the voltage only 2.5 volts. The switching voltage is different. Or if we keep the same switching voltage, 2.8 volts, we are going to result in a much lower state, which is no longer our S1 state. So here we have S1 prime state, which is only nanosiemens instead of this 200 nanosiemens. So that means here the FE FET also suffer from this minor loop switching problem. So what is the fundamental root cause for this one? So here we did some device modeling on this multi-domain switching mechanism using the phase field modeling approach. Essentially, we are going to simulate this time-dependent Landau-Ginzburg equations, essentially the partial differential equation, which describe the interaction between the domains and also the external field. So here, the key thing is that we have to assume the domains, there are multiple domains, and each domain is different in terms of the cross field, the critical voltage to flip the domain. So here, then we design those 2 loops, the larger loop and smaller loop, and run the simulations. So let's say we start the ground state, all the dipoles are up, for example, or let's say all the dipoles are down. And then in the larger loop, we are going to go through those steps and end up with this S1 state. And also in the smaller loop, we are going to end up with similar like average polarization for the S1 state. But you notice that the internal configuration is different. Even though externally you observe the same polarization value, internally the configuration is different. So here, if this is still too difficult for you to understand, let me show you a toy model, very simplified version. Let's say we have 6 domains in the system, and then they have different cursive field. So for those with larger field, we call harder domain, and then with those, let's say, smaller field, then we call easier domain. So here in the large loop, let's say initially all the dipoles are up, and then for the larger loop, first we flip 10 dipoles down, and then the second pulse is going to flip, let's say, 4 dipoles up. So we end up with 6 up and 6 down. So here in this case, the net polarization is 0. In the smaller loop, okay, minor loop, we are going to directly flip those 6 easier domains. So here we have 6 up and 6 down. So you see that internally, the distribution is different. So in the next pulse, so we're going to flip 2 more up, but here for the larger loop, we're going to flip those 2, which is harder than here we flip those 2. So that's why we need to apply a larger voltage in this case. Even though we're doing the same transition from S2 to S1, in terms of the polarization switching, the amount of switching is the same, but then the switching voltage is different. So it's very hard to track this kind of continuous switching. This is just a simple example. We only have like a few steps. But if you do the continuous training, then you have to track the history of the entire training history. Then that becomes mission impossible. So that's why here we did some simulation for a very simple like M-listed data sets. If we do not track the history, we let it go, then the training accuracy will be low. So one possible mitigation is that we always operate on the saturation loop. That means every time when we program to the intermediate state, we erase to the ground state, and then we go from here. Do not do this kind of manual tuning in the between. We always go to the ground state and then go up again. So this, of course, will bring the overhead with additional latency and energy for the erase pulse. But at least this is one possible solution for this one. But anyway, after so many trials, we believe that training might not be the immediate or let's say tangible application at this moment. So that's why we focus most on the inference of this technology. So here, another challenge we mentioned earlier is the variation, right? So here, especially when you deposit the ferroelectric thin film, as deposited, there could be different polarization. First, different phases. Second, even for the same orthorhombic phase, you may have different orientations. Then the polarization value might be different from different locations of the thin film. So here we got the data from the Fraunhofer, and then did this TKD transmission Kikuchi diffraction imaging on the as deposited thin film. And then this is the polarization map measured, let's say, across the area, like 3 by 4 micrometer square. So if you build your transistor at different locations, they may suffer from this polarization variation, right? So here then we want to evaluate the quality of this thin film without doing the entire fabrication. So that's why here we came up with some machine learning assisted TCAD modeling approach to quantify the 3 sigma of the device figure of merits of this thin film. Okay. So for example, here we create some TCAD model, and then we treat this polarization variation map as an image classification problem. Okay. So here, for example, if we build the transistor at this location, we may have this kind of polarization map in the gate area, and then this could be used as the training data set to run the TCAD, and then we get the corresponding IDVG for this kind of image map. So once we gather enough data, for example, 3,000 points of this kind of correlation between the image and then the figure of merit of the device, for example, the threshold voltage or the substrate slope or the on-state current, then we can train the neural network. So for example, we treat it as image classification problem, right? So we have this image of this polarization map, and then we correlate that with the output, which is the figure of merits of the device. So we train the model, and then after the training is complete, then we can use the model to infer the results without going through this lengthy TCAD simulation, because TCAD is very slow, especially when you run 3D with thousands of samples. It will take a few days to finish the runs. So here, then we set up this model. Of course, initially you need to gather the data. You need to spend a few days to gather the training data. But once that is done, after the model is trained, then later you can infer the result pretty quickly. So here I show some like a calibration first. Machine learning predicted results in terms of the voltage, threshold voltage versus the TCAD across 500 samples. And also here, depending on the number of data sets, for example, if we have 3,000 points in the data as a training data set, then we can have pretty good fitting between the machine learning predicted VTH versus the TCAD VTH. So then later when we do the inference, then we can just get the results in seconds in terms of those sigma of those threshold voltage, on-state current, substrate slope, and so on, given the polarization map of your thin film, right? Imagine that you change your process condition. You run a new wafer, you get the new thin film data, then we don't need to redo this again. We just of course, we have to do some in-number metrology and TKD pattern. After we get the pattern, then we can quickly run this machine learning model to infer whether this run, let's say the quality of the thin film is good enough to move to the next stage to do the further device fabrication, or we can discard this one and then fine-tune your process condition, your leading temperature or whatever, to improve the quality of your polarization variation map. Then we can basically use this as a way to speed up the material screening without doing the entire flow of the transistor fabrication. Okay, the next topic is this NV cap I mentioned earlier. So essentially, we are doing this charge domain in memory computing. So what is this? So conventionally, we have the resistive approach. As I mentioned earlier, we have this current summation from the bitline to do the dot product between the input vector and the weight matrix. So essentially, the current domain computation. And the challenge there is that when the resistance is low, especially in on-state, at least from our foundry friends, what they offer to us, the resistance is low. Therefore, when the input is high, then we are going to pass the static DC current through this resistor. So we spend a lot of static power here. But if we change this with a capacitor, okay, capacitor by its nature only consume the transient dynamic power in the rising edge or the falling edge. So we eliminate this static power. So this could reduce the power consumption significantly. And also because we do not have the current through, then the IR drop also mitigated. And then for the capacitor, because we get rid of the excess transistor, we can do the multi-tier 3D stacking more friendly. So that's all the benefits we can, imagine from here. Of course, then the challenge here is how to engineer this capacitor. Basically, we are going to create different capacitance states to encode the data. Instead of using the resistance to encode the data, we're going to use the capacitance to encode the data. And essentially, we are going to do this computation in the charge domain. So here we do the charge transfer process, and then we will show you the output voltage is proportional to the input voltage multiplied by the capacitance of this crossbar array, modulated by the reference cap at the edge of the array. So this is our vision. And then we started from this simple MFM cap. So this is nothing special here, tinitrate HZO and tinitrate. So ideally, if you look at the MFM cap, then the butterfly curve, or let's say the PV loop, should be symmetric. Or let's say CV loop should be symmetric because you have two plates, and then there's no difference, the top plate and bottom plate. Then if you do the CV measurement, small signal CV measurement, it should be symmetric respect to 0 voltage. But somehow in this device, we see that here the butterfly curve is distorted. Right? We create a symmetry in the CV. Therefore, at 0 voltage, we have high capacitance state and low capacitance states. We're going to use that as a mechanism to encode the data. So here we can keep cycling for like more than 10,000 cycles. And then here we suspect here in this particular sample, we have some asymmetry in the interface properties here. Because we have plasma enhanced process here, we may damage the bottom interface a little bit. Then we have more oxygen vacancy at the bottom interface. That could pin some of the domains always up, even after the forward sweep. So if we have the pinned domain after the forward sweep, then when we do the small signal CV measurements, we are going to dump more charges on the plate because of the domain wall motion here. You have the expansion of the domain under the AC excitation. Then we are going to have more charges on the plate. More charges on the plate is translated as higher capacitance. Okay. So then in the negative sweep, then we don't have the domain wall, then we have less charges. So this is, of course, a hypothesis. We have done some modeling and to back up this mechanism, but of course, there's no direct evidence. Right? This is what we assumed. But anyway, we can successfully create this window, even though it's kind of small, but we can have high and low capacitance states. The key is to have the CV asymmetry, okay? So with this device, we further integrate that into a crossbar array. And with a probe card system, we can demonstrate some of those charge domain transfer mechanism we proposed earlier. So ideally, we should have some like op-amp as edge of the array to do the charge transfer process, but we don't have the integrated CMOS on chip. So that's why we have a Bucky system with the circuit board, a probe card, and then switch matrix and so on. But anyway, we have this setup in our lab. So we can experimentally measure. Let's say we turn on multiple rows. We have multiple voltages come in, and then turn on multiple rows. And which first step is to charge the array from, let's say, horizontally. And then second step is to transfer those charges to the outside through the op-amp. There is a reference cap on the op-amp. So essentially, then the output voltage will be the total amount of charge we transfer from the array divided by the reference cap value. And then here in this experiment, we demonstrate that the output voltage is linearly proportional to the number of cells that is in the high capacitance state along the column. So we verified that at least this mechanism is working in this small setup. And then we further did some benchmarking. Let's say if we scale up the system, right, because we only have like 8 by 8 or 10 by 10 small array in the experimental setup. But if we scale up to 128 by 128 by simulation, then we can demonstrate that the energy to do this kind of charge domain computation compared to the resistive counterpart, then the energy is much lower, like 20 to 200 times lower compared to other competing technologies. So of course, the limitation of this one is we have to consider the thermal noise, because if a system is full of capacitance, it suffers from the thermal noise. KT over C is your thermal noise. So here we consider the thermal noise in the transient simulation, and then consider the swing of the dynamic range of the op-amp, and then this can get us this signal-to-noise ratio. And then in this case, the ENOB, the effective number of bits, is like about 4, which is not ideal because here 128 by 128, at least you should get 7 bits, but here effectively you only get 4 bits. So then what is the challenge here? The challenge is the on-off ratio of our device is very small. The on-off ratio is less than 1.2. Let's say high capacitance divided by low capacitance is only 1.2. So the margin is so small. So then how to increase the on-off ratio? So initially we have this MFM cap. It's like a symmetric structure, right? If you want to get more asymmetry, we have to change the structure to be more symmetric. So that's why we went on to this MFIS cap. And since we have collaboration with GlobalFoundries, we tested their FE-FET in this NV cap mode. So what we did here is to, let's say, measure the CGS and CGD where the S and D is connected. So the key is that we cannot connect the body together. If we connect the body together, then this is like a normal setup. So here we have to use another terminal to ground the body. Okay. So if we do that, then this is a CV curve. The blue one, you will see that here we create a very large window at 0 voltage. So this window is larger than 20, I believe. So what is the mechanism of this FE-FET in this mode? So here, this is the cartoon figure for the physics. So if the device is fully programmed, all the dipoles are done, when we measure the CGS and CGD, because the channel is formed, we are going to measure entire inversion cap plus the overlap cap. So this is high capacitance state. And then if the dipoles are all up, then the channel is depleted. Then when we measure the CGS and CGD, we only have the overlap capacitance. So we verified this mechanism by some measurements. First of all, if this is true for the on-state, the on-state capacitance should be proportional to the gate area, which is verified by the experiments here. And then the off-state seems to be related to the overlap length. And then depending on the gate length, then the C off is proportional to that. So then at least from the measurement, this supports this hypothesis. And then we went on from the TCAD modeling point of view. We also verified the working mechanism, and we can reproduce the CV from the TCAD simulation. And you see that this agrees with experiment. We can look at the electron density and look at the inversion and accumulation depletion mode, and then we measure the CV, then that will match what we proposed. So here, then the challenge, as I mentioned earlier, the variation, right? So then, depending on the cell-to-cell variation and thermal noise, then the output voltage may fluctuate. So that may cause some inference accuracy degradation at the system level. So we have to incorporate that into the inference accuracy estimation. So that's why we set up this framework from devices to the system. We look at the impact of on-off ratio, device-to-device variation, and then the charge transfer time, and then the thermal noise variation, and so on, to look at what is the inference accuracy if we use this technology, right? So then here are some results. I quickly show you that. It's a design space exploration problem because we have so many parameters to affect the accuracy. But here, for example, you see that the on-off ratio matters. If you have on-off ratio only 2, then the accuracy will be bad. But if you improve the on-off ratio, the capacitance window over like 13, then you can get good accuracy. And also this depends on how many rows you turn on simultaneously, and what is the op-amp, the output swing, and what is the on-off ratio. So here we want to get this region, so we have to co-optimize those design parameters to ensure that the accuracy is acceptable. Of course, this is a small model. I believe it's for CIFAR 10 data sets. For ImageNet, this will be more stringent. So this is just an exercise to show you how to quantify the device level parameters into the system level metrics. So here, the next step, we show you the FEFET from the Global Foundry, essentially the front-of-line process. But we are interested in the back-of-line integration with the MFS NV-cap. So that's why we take advantage of this oxide semiconductors as a semiconductor as a back-of-line. So here we have the HZO and IWO, which is indium tungsten oxide, which is all ALD processed. So here I will skip the details, but we are going to present the results in the upcoming IEDM, so we can improve. We can also maintain like more than 20 on-off ratio, but fully with the back-of-line processing now. Next topic, very quick. So we also see opportunity as a back-of-line using the FEFET as the routing switch. So we can have the reconfigurable interconnect to map different AI models. So this is in principle with FPGA, right? You have the routing switch for the FPGA, but the FPGA's standard routing switch is like SRAM control a pass gate. So here you have 7 transistors at least. So what if we replace the routing switch with FEFET as a back-of-line? So FEFET, when you program it to high VTH state, you can block the signal passing through. If you program it to the low VTH state, you can allow the signal to pass. So here we built some 4-way router with the FEFET as back-of-line, and then we test the routing capability in terms of the signal passing and blocking. We have to do it in the GSG kind of RF probing kind of setup to look at what is the cutoff frequency. So here in this example, for example, we can pass the signal up to 12 gigahertz for the back-of-line routing. So this is another way to use FEFET for the routing of the signal as a back-of-line. So we don't need the front-of-line SRAM and pass gate in this case. So one challenge of this routing switch is that we have to deliver enough current to ensure fast signaling. So one challenge with the back-of-line oxide semiconductor channel is that the mobility is intrinsically lower than that of front-of-line silicon. So here, to be competitive, we have to increase the drive current density per footprint. So here we are going to make the stack nanosheet for the indium tungsten oxide. So this is a collaboration work with Shimeng, and we recently developed this channel release process for the IWO back-of-line transistor. Therefore, here we can get very high current density, like about 500 microamp per micrometer, at the logic compatible voltage, 1 volt. So again, we're going to present this work in the upcoming IEDM conference. Okay, the last topic, a few minutes left. So we're interested in the 3D VLAN with FE-FET. This is another avenue for the Ferro to be used in the 3D VLAN setting. So here, the motivation for us is to do this genome sequencing. We have some collaborations with Professor Diana Rosin from UC San Diego, where she did a lot of genome sequencing acceleration. So the challenge here is that the database are booming. So let's say you have like hundreds terabytes data in the genome sequencing. Then the data is stored in the SSD, essentially 3D NAND. Normally, you have to load the data from the 3D NAND to the DRAM to the processor. Then you match with your new unknown sequence. So this is a lot of data movement. Why do we just do the data matching near the storage without moving the data from the storage to the processor? So that's some motivation here. So here, the hyperdimensional computing could be a potential solution for that. Essentially, we do the pattern matching without moving the data. That's the key. So here, for the 3D NAND, we can do this, okay? Assuming that your genome database is pre-stored in the 3D NAND, then what we do is to create this query vector from the bit line, and then we're going to compare this query vector with what you pre-stored. For example, here, in these 3 strings, we're going to compare the data. Only one string is matched, so you turn on one string, so you get one copy of currents. And then in another example, you are going to have here 2 copies, let's say two match string. You are going to get higher currents. So here you can do approximate search as well, depending on how many matches you have from the strings. Then you can use preferred circuits like ADC and comparator to determine which one you have the most match. Then that is what you are going to infer. So this is like a 3D NAND approach. But then the challenge here is that 3D NAND, the industry is a very close circle. They will not, the vendors like Micron, Samsung, will not allow you to modify the preferred circuits to do this job. So then the challenge here is how do we integrate those preferred circuits? We modified here, for example, additional ADC, comparator, and another logic. So here the solution is heterogeneous 3D integration, right? So we can design those preferred circuits in another logic die, and then we can do the bonding with the 3D NAND. So 3D NAND industry will adopt this X stacking anyway. They're going to integrate with another logic die. And why not we design some preferred circuits in another logic die and then do the bonding? So this could be some potential pathway moving forward. So how could Ferro help in this application? So here the Ferro has much lower program and erase voltage and read voltage than the charge trap based NAND. Therefore, we can further reduce the energy and latency for this kind of pattern matching problem in the 3D NAND. I've skipped the details due to the time limit here. And the last slide. So here, one challenge for the Ferro, if we use it for the NAND, the memory window is kind of small. And then how do we increase the memory window in the FEV NAND? So here the idea is to do the gate injection. So for the charge trapping, actually it's harmful to the FE-FET if the charge trapping coming from the channel side, because the charge trap transistor, the switching direction is opposite to the Ferro. The Ferro is counterclockwise in terms of IDVG, and then the charge trapping is clockwise. So if you do the charge injection from the gate, actually those two effects will add up instead of conflict with each other. So here the key is that we have to design some interface from the gate side to allow the charge injection to the ferro. Then we can boost the memory window. For example, in this case, we can create the memory window up to 6 or 7 volts if we can have this kind of charge injection layer from the top. All right, so I will quickly summarize. We talked about 4 problems, or let's say applications for the FE FETs. First one, we talk about the minor loop in the multi-level programming, and we see this is a challenge, and also the variability in multi-domain switching is also a challenge moving forward. And then we figure out some new ways to use a ferro. For example, this NV cap to allow the charge domain computation, which maximizes the energy efficiency because we do not spend the static power consumption. And then the background line integration opens new opportunities. For example, the routing switch with a ferro gate, then we can allow this reconfigurable interconnect. And also, lastly, we can renovate the 3D VLAN with a ferro gate stack with enhanced memory window, and then we can use this for in-memory search. So with this, I'd like to thank my collaborators, especially Professor Sumandata and Asif Khan, on our joint efforts in the ferro, and also all the sponsors. I have many sponsors on the ferro programs. I will not talk all of them, but yeah, thank you.
Fantastic talk. All right, questions? Let me give you a microphone because we're zooming this thing the world at large.
You were first.
Go ahead.
Hello. Thank you very much for the talk. It was really nice. I was involved on these kind of topics for all my PhD thesis. So I would like to ask you a couple of things really fast. The first one is when you talk about the capacity crossbar and so, how do you avoid the leakage discharge or the snake path problems? You have it in the slides 23 if you want to go there.
So in the capacitive crossbar array, we don't think the snake path is significant because in the DC mode, then you do not have the path, right? Leakage path. So here what is challenging actually is the disturb, because we still have the disturb issue, half select issue. So when you program, or let's say program the selected cell, then some of the cells will have half of the programming voltage. So we still think that half voltage disturb will be a problem. But I don't see any significant leakage path through the unselected cell, because essentially they are open circuit.
Yeah, but when you place the voltage, you charge this capacitor and you have another capacitor in series, right?
So actually, we take advantage of that because we turn on all the rows and all the columns. Then we're going to charge up all the rows, and then we transfer all the charges out. This is how we get this weighted sum, actually.
Okay.
Yeah.
Okay, thank you.
Of course, the parasitic wire capacitance will affect the accuracy of the weighted sum. Yeah.
Thanks for a great talk. So actually, I have a related question. In my understanding, when you have a high frequency system, then the parasitic effect will be very severe. Then how will that affect the accuracy of this capacitive crossbar array?
Yeah, we did a simulation on the speed, and we do need some time to transfer the charges out. If you have any residue of the charge, not transfer out, then that will affect your accuracy. So here the speed actually will be a little bit slower than the resistive approach, but at least we get like 20 nanoseconds for like 128 by 128 array with reasonable like a cell size, like 80 nanometer by 80 nanometer kind of dimension. So we can get like 20 nanoseconds to fully transfer the charges out.
Okay, thank you.
More questions? Questions? I have a question. So you showed us how you are using the small signal capacitance in this case to capture the weight. You showed us the high capacitance and the low capacitance, the two extremes, but it wasn't clear to me how you program the intermediate values of capacitance.
Okay, yeah, we didn't show that. First of all, for this initial work, because on-off ratio is so small, we only have 2 levels. But then with this global foundry wafer and also our in-house back-of line and capacitor, then we just change the programming voltage. We can get the intermediate states.
Wouldn't you have the same issue that you highlighted at the beginning of your talk?
Yes.
Depending on the history of programming, you will end up with in a different place?
Yes. But if we do the inference, then what we care about is we always operate on the saturation loop, right? We do not, let's say, you can always go to the ground state and then accurately program to the S1, S2, S3.
Yeah.
If you do not allow S1 to S2 transition, you can avoid this minor loop issue.
Yeah.
So you always go to the ground state and then you change the programming voltage. You can end up with different intermediate state. Of course, we may have to do some verify. If you overprogram, then you have to fully erase. Do not try to fine tune there. Always fully erase and then retry it again. Yeah.
More questions? Yes.
Thank you very much for an exciting talk. So with regards to the scalability of the capacitive array, what's your vision on that? How far can we get?
Okay, that's a very good question. So I didn't show that. The smallest size we measured from the global foundry wafer is 1 micrometer by 1 micrometer, and then the memory window is still reserved there. On-off ratio is more than 10, and everything looks good. But below 1 micron by 1 micron, we don't know. The reason is that it's impossible to measure it from off-chip. Below femtofar, the lowest floor of your CV measurement system cannot allow you to measure anything off-chip below femtofar. So that's why we are right now designing an on-chip circuitry taped out through global foundry to measure this effect with nanoscale capacitor with global. This is still ongoing. We don't know experimentally, but then from simulation, of course, we can assume this on-off ratio maintain with the scaling. But if you ask me that experimentally, we don't know, frankly speaking. But I tell you, the only way to verify it is to integrate on-chip circuitry to measure anything below femtofar. Let's say tens of attofar, you have to use on-chip sense amplifier. Yeah.
Very nice. How about the scalability in terms of the number of cross points you can have? Like the 128 by 128 now. How far do you see this go?
Okay, so then that depends on the on-off ratio of the device. The larger on-off ratio, you can allow a little bit larger array. But also at the same time, we have to take care of the thermal noise. We have to run the transient simulation of the entire system to evaluate the impact of the thermal noise. So the scalability, as I mentioned, for this 128 by 128, 50 nanometer by 50 nanometer of the cap seems okay. The KT over C will give us maybe 2 millivolts, 3 millivolts at room temperature in terms of the fluctuation of the output voltage. So if you further scale, then the capacitance, the thermal noise will be up. But of course, you can take some advantage of the 3D trench capacitor. Then you can use surface area and then increase the capacitance without increasing the footprint. Then you can mitigate some of those challenges. Yeah.
Thank you very much. Thank you.
Wonderful. Let's stop at this point. Thank you again, Shimeng, for
Thank you.
really excellent talk.